Alright, let's go. Number 10. The blind spot filling-in effect. In 1668, a French physicist named Edmé Mariotte was dissecting eyes in his lab in Dijon, tracing the anatomy of the optic nerve. He was not studying consciousness, he was mapping tissue. But he noticed something strange in his own vision when he closed one eye and stared at a spot on the wall. A coin-sized region where objects simply vanished. He had found the hole. Every human eye has one. Where the optic nerve exits the retina, there are no photoreceptors. 0. The standard model of vision says you should see a black gap in your field of view roughly the size of 9 full moons stacked side by side. Right now, in this moment, there should be a missing piece. But there isn't. The brain patches it, not with black, not with static. With whatever pattern surrounds it, wallpaper, sky, the face of the person you love, invented and pasted seamlessly into the visual stream. V. S. Ramachandran and Richard Gregory published a landmark paper in Nature in 1991 titled Perceptual Filling In of Artificially Induced Scotomas in Human Vision. They showed the fill-in was not passive interpolation. It was active fabrication. Subjects reported textures, motion, and colors in regions where no signal existed. Every proposed explanation has failed to close the case. Simple neural averaging doesn't account for complex texture completion. Higher order inference can't explain how it happens below conscious awareness. Predictive coding, formalized in Carl Friston's work at UCL, elegant, but no one has isolated the exact circuit doing the invention, which means the image you are seeing right now, the screen, the room, your own hands, contains a patch of pure fabrication, manufactured on the fly, presented to you as reality. You cannot find it. You cannot see the seam. If part of your vision is invented every second and you cannot detect it, how would you ever know which part? Every entry today reaches deeper into the same wound. Number 9. The McGurk Effect. In the mid-1970s, a developmental psychologist named Harry McGurk at the University of Surrey was studying how infants match voices to faces. He and his research assistant John MacDonald were preparing stimulus tapes, dubbing audio of one syllable over video of a mouth shaping another, for a study on speech perception in babies. Routine editing work. Preparation, not experiment. The standard model of speech perception said the ear does the hearing. Light enters the eyes, sound enters the ears, and the two are processed independently before being combined at higher stages. Vision might help you follow a conversation in a loud room, but it should not overwrite what the ear reports. Signals travel through separate cranial nerves, separate cortical regions, separate paths. Then McGurk and MacDonald played the mismatched tape back and heard a syllable that was not on the tape at all. Their 1976 Nature paper, titled Hearing Lips and Seeing Voices, described the effect precisely. Audio of ba, dubbed onto video of a mouth articulating ga, produced a phantom da in roughly 98% of adult listeners. The heard syllable existed on neither track. It was generated. Manufactured. Voted into existence by a committee of senses. Every attempt to dissolve the effect has failed. Attention hypothesis? Subjects remain fooled even when told exactly what is happening. Learned association from language exposure? Newborns show early forms of the same integration in studies by Kaisa Tapana and colleagues. Auditory imagination? fMRI work at the University of Cambridge showed activation in the primary auditory cortex itself. The ear region is being rewritten, not overruled. Which means what you hear in every conversation you have ever had is not what reached your ears. It is a fused output, a negotiated compromise between eyes and ears. Sometimes wrong. Your entire linguistic life has been consumed inside a hallucination that shows no seam. What else are your senses agreeing to lie about? Each glitch below sits deeper in the brain than the last. Number 8. Phantom limb pain. In 1866, a Union Army surgeon named Silas Weir Mitchell was treating amputees returning from the American Civil War at Turner's Lane Hospital in Philadelphia. He was cataloging wound care and infection outcomes. standard military medicine. He was not looking for a philosophical monster. He found one in almost every ward. Pain, by the standard model, requires tissue. Nociceptors in skin and muscle fire signals up the spinal cord. Damage a nerve, sever a limb, and the signal source is gone. The pain should stop. The map should catch up to the territory. This is the model taught in every medical school for a century. Mitchell's patients felt their missing limbs in agony. Some described fingers clenched into fists they could not unclench. Some felt the exact sensation of the wound that took the limb, replayed on loop in a hand that no longer existed. Vilayanur Ramachandran and Diane Rogers Ramachandran published a 1996 paper in Proceedings of the Royal Society B titled Synesthesia in Phantom Limbs Induced with Mirrors, documenting relief through the now famous mirror box, a device that used reflected sight of the intact limb to trick the brain into unclenching a fist that was not there. Every proposed cause has been ruled insufficient. Peripheral nerve stumps? Patients born without limbs still report phantoms, documented by Ronald Melzack at McGill. Cortical reorganization? Real, mapped by Tim Pons at knee in 1991, but does not explain the specific texture of the pain. Pain memory? Fails to account for phantoms that appear months after clean surgical loss, which means the body you feel, the shape of your arms, the position of your legs, is not read from your body. It is read from a map inside your head. And that map does not always update when reality changes. It just keeps drawing. If your map outlives the flesh, which of the two was ever really you? The next glitch reroutes senses that should never touch. Number 7. Synesthesia. In 1880, the polymath Francis Galton published a short paper in Nature titled Visualized Numerals. He was cataloging mental imagery in ordinary people, how they pictured calendars, numbers, dates, population scale curiosity work, not neuroscience. In his questionnaires, a small subset of respondents reported something Galton could not fit into any known category. They said they saw colors when they heard letters, that numbers had positions in space. That Wednesday tasted metallic. The standard model of sensory processing held that the senses were modular. Sight in occipital cortex, hearing in temporal, taste in insular. The pathways were separate. Crosstalk was rare, pathological when present, and adult onset only under lesion or drug. Ordinary healthy brains did not blur the channels. Galton's respondents were not lesioned. They were not drugged. They had been experiencing merged senses their entire lives and had assumed everyone else did too. Julia Simner and her team at the University of Edinburgh published a study in the journal Perception in 2006 titled Synesthesia, the Prevalence of Atypical Cross-Modal Experiences. Their large sample screening put the incidence of at least one form of synesthesia at roughly 4.4% of the population, one person in every 23. Every attempt to explain it as ordinary cognition has fallen apart. Metaphor? Fails against fMRI studies by Jamie Ward and colleagues showing genuine V4 color area activation for heard sounds. Learned association from childhood alphabet magnets? Cannot explain the highly stable involuntary pairings that persist for decades. Genetic linkage? Real, Simner's group has mapped familial clustering, but no single gene has been isolated, which means the boundary between your senses is not a wall. It is a curtain. And in a measurable fraction of people, the curtain is thinner or torn open entirely, with no damage, no illness, no cause. If your senses are separate only by convention, whose convention did you inherit? Now the glitch turns to what you fail to see. Number 6. Change blindness. In the mid-1990s, a young cognitive psychologist named Daniel Simons at Cornell was studying attention, specifically how much visual detail people actually process from a scene. He was designing experiments with photographs and short film clips. The work was aimed at classroom psychology, not the foundations of consciousness. He kept finding that his subjects were quietly, catastrophically bad at noticing things. The standard model of visual attention held that we build a rich, detailed internal representation of the world. We look, we see, we store. If something in the scene changes, a person, a wall, a car, the change is compared against the stored image and detected. This is the intuition every human being has about their own vision. It feels obviously true. Then Simons ran the door study. Simons and Daniel Levin published a 1998 paper in Psychonomic Bulletin and Review titled Failure to Detect Changes to People During a Real-World Interaction. An experimenter stopped strangers on a college campus to ask for directions. Mid-conversation, two workers carried a large door between them, briefly blocking view. During the interruption, the original experimenter was swapped for a completely different person. Different height, different clothes, different voice. Roughly 50% of the subjects continued the conversation without noticing. Every softer explanation has failed to survive replication. Inattention alone, subjects were engaged and looking directly at the face. Poor memory, the swap happens within seconds. Sparse representation of strangers, the effect holds even with prolonged exposure in follow-up studies by Ronald Rensink at UBC. Which means the world you feel confident you are seeing is a low-resolution sketch that your brain touches up only where you happen to be looking. Everything else is assumption, filled in from prior belief. Somewhere between waking up and now, something around you changed, and you did not see it. The next glitch changes what counts as your body. Number 5. The rubber hand illusion. In 1998, Matthew Botvinnik was a graduate student at the University of Pittsburgh working with the cognitive neuroscientist Jonathan Cohen. He was studying self-representation, the way the brain keeps track of which body parts belong to it. The project was procedural and slow. Then, almost as a side demonstration for a colleague, they set up a table with a lifelike rubber hand. The standard model of body ownership required a triangulation of proprioception, visual confirmation, and touch, a stable agreement between where your limb is felt, where it is seen, and what it is sensing. Break the agreement and ownership breaks. Restore it, and ownership holds. The self was thought to be tethered firmly to living tissue. Botvinnik sat subjects with their real hand hidden behind a screen and the rubber hand placed in front. 2 paintbrushes were stroked synchronously, one on the fake hand in view, one on the real hand out of sight. Within about 90 seconds, subjects began to feel touch in the rubber hand. Some flinched when it was threatened with a hammer. Galvanic skin response spiked as if their own hand were under attack. The paper appeared in Nature in 1998, titled Rubber Hands Feel Touch That Eyes See. It has since been replicated hundreds of times across ages and cultures. Every attempt to reduce the effect to something less unsettling has failed. Imagination? Skin conductance response is autonomic. It cannot be faked. Suggestion? Control conditions with asynchronous stroking eliminate the effect, ruling out expectation. Placebo? Physiological threat responses are not placebo effects, which means the boundary of your body. The place where you ends and not you begins is not fixed to your skin. It is negotiated in real time by the brain using whatever evidence is nearest. Show it the right signals and it will adopt a stranger's hand. Show it the right room and it may adopt something else entirely. Now the glitch reaches memory itself. Number 4. The neuroscience of déjà vu. In the early 2010s, Akira O'Connor at the University of St. Andrews wanted to do something almost no one had done, trigger déjà vu deliberately in a scanner. He built controlled memory tasks in virtual reality designed to create the exact conflict between recognition and recall that seems to underlie the experience. He was not chasing the paranormal. He was chasing a signal. The standard model of familiarity said the sense of I have seen this before is generated by the hippocampus and surrounding medial temporal lobe. When those regions detect a match with stored memory, they emit a familiarity signal, and consciousness reads it as recognition. In this model, déjà vu should be a hippocampal misfire, a false positive from the memory system. O'Connor's fMRI results did not show that. O'Connor and colleagues presenting at the International Conference on Memory in Budapest in 2016 and in subsequent journal work reported that during induced déjà vu, activity was elevated not in the hippocampus, but in frontal decision-making regions, as if the brain were auditing its own memory system and flagging an error. Every earlier explanation has crumbled under scrutiny. Temporal lobe microseizure, first proposed by John Hewlings Jackson in the 19th century, real in epileptic patients but does not account for déjà vu in healthy adults. Dual processing failure between recognition and recall, proposed by Alan Brown at SMU, elegant, but not yet mechanistically pinned down. Rhinal cortex misfire, suggested but not confirmed in scanning data, which means the moment of déjà vu is not a memory speaking. It is a supervisor speaking. Some inner watchdog quietly telling you that your memory system just produced something it does not trust. You feel a familiarity, and then a second deeper system tells you the familiarity itself is false. Both signals reach you at once. Both feel like yours. If the machine that flags false memories is real, how often does it stay silent? The next glitch strikes what you thought were basic facts of light. Number 3. Visual illusions that defy known optics. In 1839, the French chemist Michel Huguenet Chevreul, director of the dye works at the Gobelins tapestry factory in Paris, was troubleshooting a complaint. Weavers were returning threads as the wrong color. The chemistry of the dye was fine, the threads were fine, but when placed next to certain neighbors on the loom, the same yarn looked utterly different. Chevreul was fixing a manufacturing problem. He ended up inventing a discipline. The standard model of color said perceived color tracks wavelength. Photons of a given frequency strike the retina, cones respond, the brain reads out the value. Same light, same color. Different light, different color. Simple. Then Edward Adelson, at MIT's Department of Brain and Cognitive Sciences, published his checker shadow illusion in 1995. Two squares on a checkerboard have identical grayscale values, measurable at 120 out of 255 with any photometer. One sits in shadow. To every human viewer, they look completely different. One clearly dark, one clearly light. Every reduction of the effect to lower-level mechanics has failed. Retinal adaptation cannot explain effects that hold in brief single glances. Simple cognitive judgment fails when subjects report the effect even while knowing the truth. Discounting the illuminant, the model advanced by Alan Gilchrist at Rutgers, powerful, but still contested, and cannot fully account for edge cases in Anderson and Winover's 2005 Nature study on lightness perception. Which means every color you have ever seen has been an inference, not a measurement. A best guess, assembled by your brain from surrounding context, ambient light, and prior expectation. You have not seen red. You have only ever seen your best explanation of red. If the world you perceive is a hypothesis, when did you last check it against anything real? The next glitch stretches something you thought was untouchable. Time itself. Number 2. Time perception distortion under stress. In 2007, the neuroscientist David Eagleman at Baylor College of Medicine wanted to answer a question that had lingered in the literature for a century. Does time actually slow down in life-threatening moments? Survivors of car crashes, falls, and violent accidents describe a stretched, cinematic quality to the seconds involved. Eagleman decided to test it rigorously. He dropped people from a tower. The standard model of subjective time held that if people report time slowing down, then their temporal resolution, the frame rate at which they experience the world, must actually be increasing in that moment. If true, you would be able to read faster, see faster, react faster. High adrenaline should sharpen the very clock of consciousness. Eagleman rigged a device called a perceptual chronometer, a small wristwatch that flashed digits too fast to read at normal speeds. Then he sent volunteers into a 31-meter controlled freefall onto a safety net in Dallas. If the world truly slowed down, they should be able to read the digits mid-drop. They could not. Chess Stetson, Matthew Fiesta, and David Eagleman published the study in PLOS I in 2007, titled "Does Time Really Slow Down During a Frightening Event?" Subjects overestimated the duration of their own falls by roughly 36%, but their in-flight visual reading speed was no better than at rest. Every alternative has failed to save the intuition. Genuine perceptual speed-up, ruled out directly by the chronometer. Adrenaline-driven cognitive sharpening, real, but does not stretch time. The remaining explanation, memory density, says the brain records the frightening moment in unusual detail, and later, replaying that dense memory, mistakes the density for duration. Which means the slow-motion memory you carry from the worst moment of your life is not what you experienced. It is what you reconstructed afterward. Your most vivid memories may be the ones most rewritten. The final glitch reaches the thing you have never doubted, the location of yourself. Number 1. Out-of-body illusions. In the mid-2000s, 2 labs in Europe were quietly closing in on the same question from different sides. Henrik Ehrson at University College London, later at the Karolinska Institute in Stockholm, was studying body ownership. Bigne Langenhager in Olaf Blanc's lab at the École Polytechnique Federale de Lausanne was studying self-location. Neither team was chasing mysticism. Both were building rigs of cameras, goggles, and paintbrushes. The standard model of the conscious self placed it, essentially, behind the eyes. The eye that watches was assumed to be locked to the body, anchored by the constant integration of proprioception, touch, and vision from a first-person origin. Out-of-body experiences were treated as hallucinations, dreams, or pathology, not something you could induce in a healthy adult on a laboratory schedule. Then both labs did exactly that. Earson's 2007 paper in Science was titled "The Experience of Body Ownership Shifts to an Artificial Location." Langenhager, Toddy, Metzinger, and Blank published a companion paper in Science that same year, titled "Video Ergo Sum: Manipulating Bodily Self-Consciousness." Subjects wore head-mounted displays showing a live video feed of their own back from 2 meters behind. The experimenters stroked the subject's real chest and the visible virtual back synchronously. Within seconds, subjects reported that they had drifted backward, that the self was now standing behind the body they were watching. Every softer reading has failed. Hallucination? The effect is reliably induced and switched off by asynchronous stroking. Suggestion? Robust and naive subjects who were not told what to expect. Sensory conflict alone? Present, but does not explain the specific relocation of the felt self to a coherent alternative origin point. Which means the point in space from which you experience being you is not a fixed feature of your body. It is a construction. Movable, overwritable, right now, with the right hardware, the observer inside your skull can be walked across the room. If the seat of the self can be relocated by a paintbrush and a camera, was it ever really seated anywhere? Every glitch on this list lives not at the frontier of neuroscience, but inside its most confident textbook chapters. Vision, hearing, body, memory, time, self. The more precisely we measure each mechanism, the more of the person disappears into the machinery. The universe is not confused about what you are. We are. If you want to see more videos like this, click the video on screen now.